Hello and welcome to podcast.init, the podcast about Python and the people who make it great. I would like to thank everyone who supports the show on Patreon. Your contributions help to make the show sustainable. When you're ready to launch your next project, you'll need somewhere to deploy it, so you should check out Linode at podcastinit.com/Linode and get a $20 credit to try out their fast and reliable Linux virtual servers for running your app. And now you can deliver your work to your users even faster with the newly upgraded 200 gigabit network in all of their data centers. If you're tired of cobbling together your deployment pipeline, then it's time to try out GoCD, the open source continuous delivery platform built by the people at ThoughtWorks who wrote the book about it. With GoCD, you get complete visibility into the life cycle of your software from one location. To download it now, go to podcastinit.com/GoCD. Professional support and enterprise plugins are available for added peace of mind. You can visit the site at podcastinit.com to subscribe to the show, sign up for the newsletter, and read the show notes. And if you have any questions, comments, or suggestions, I would love to hear them. You can reach me on Twitter at podcastinit or email me at hosts@podcastinit.com. To help other people find the show, please leave a review on iTunes or Google Play Music, tell your friends and coworkers, and share it on social media. Your host as usual is Tobias Macey, and today I'm interviewing Rohit Pandey about PyRay, a 3D rendering library written completely in Python. So, Rohit, could you start by introducing yourself?
Sure. So, currently for my day job, I work as a data scientist for Microsoft Azure, Azure being the cloud service that Microsoft offers. Throughout my professional life, I've been working in statistics and analytics profiles. And while I was doing my master's in operations research at Columbia, I heard of this cool new field called data science. This was back in 2013, so it was still kind of new at that point. So I was immediately drawn to it. So I like kind of applying math to real world problems, and that's what I've been doing for a living for a while. As you mentioned, Tobias, in my free time, I like to do some other cool projects that also involve either learning about math in some way or applying it to the real world. So one such project was PyRay, which involved making nice visualizations, and we'll obviously get more into that in the rest of the podcast. So yeah, that's me.
And do you remember how you first got introduced to Python?
Yeah, when I first, my very first programming language was R. So this was when I was in working for a company called Nielsen, which was a market research company, and that was kind of the most popular open source language that was used. And then slowly I started running into the limitations of R and with respect to memory and that kind of stuff and performance. So then I started getting drawn to languages like Java and C#. At some point, I was just introduced to Python. I didn't catch on to it immediately. Initially, I was used to the whole structure of having the curly brackets and all that stuff, and just having indentation and stuff didn't immediately appeal to me. But later I found that it was just the perfect mix of like a scripting, like it was a scripting language, so you didn't have to compile your code every time, and you could iterate fast that way. And then with the added benefit that it was actually it wouldn't break if you were handling data that was larger than your computer's memory. So slowly I got more and more drawn to it and found that it was just perfect for my use case. And I've fallen deeper and deeper in love with it since, because I later realized that you can do almost anything in Python, right from serving websites to building complex math models, to creating visualizations and manipulating images and stuff. So and as we all know, it's gaining in popularity all the time. So yeah, that's kind of my story of how I got introduced to and warmed up to Python, and it's now definitely my favorite language.
And now that you've been using it for a while, you mentioned that you started working on PyRay as a hobby project for being able to do 3D rendering of mathematical models using pure Python. So I'm wondering if you can explain a bit about what PyRay is fundamentally and maybe some of the other tools that it compares to, and then what motivated you to create it, particularly using pure Python as opposed to some of the other existing libraries that lean more heavily on compiled languages.
So first, what is PyRay? And I'd like to invoke this image first of all. So we know that our eyes are basically these two-dimensional sheets, right? Where we have these kind of planar images that form on them, and so obviously we have no trouble grasping 2D objects. We kind of grasp them almost immediately. And then when we look at something that's three-dimensional, and imagine like holding like a complex three-dimensional object in your hand, the first thing you're going to do is just going to start, turning it around, looking at it from different angles, and just kind of visually exploring it. So that's kind of a natural, the natural way that we explore objects that are higher than two-dimensional. And right now, I mean, obviously, which is three, because we live in a three-dimensional world. So that's how I like to fundamentally think about PyRay. Taking three or even higher dimensional objects and rotating them around, and seeing how how the view of this object changes, and in the process getting a feel for the properties of the object, and having our brains kind of process intricately what the object is like, what its shape is, etc. So fundamentally, I think of PyRay as a library for doing just that. Instead of doing it physically, you do it on a computer with Python. You take an object and you slowly rotate it in whichever way you want, and that kind of gives you some insight into it. And I think kind of that itself it sounds simple, but you can get lots of very cool visualizations, and also very good insights with just this simple approach. So now moving on to the second part, what motivated me to build PyRay, and why did I choose Python? So actually, the first inspiration for me was, I saw this video on YouTube, and it was on a channel called 3 Blue 1 Brown, and that video was titled Music and Measure Theory. So I was just really impressed by it. Even before I saw that video, I had been imagining creating this visual feel for mathematics, but when I saw it, I immediately knew that I wanted to do something similar. And this was by a guy called Grant Sanderson, and he had a tool written in Python. So I went and tried to use his tool, and his tool, by the way, is called Manim, MANIM, and I believe it stands for Math Animations. Now, when I tried to get his tool set up, he made it very clear, like on GitHub in the README file, that it was primarily for his process of making mathematical animations. It wasn't meant to be a tool that people could kind of pick up and just start using straight away. It depended on some libraries that were not being maintained anymore. So this is kind of, in that way, I decided to create a new tool that completely diverged, which was the complete opposite of this Manim, which was Grant's tool, in terms of using kind of the latest libraries, and designing it in such a way that users could just pick it up and run it with minimal effort. Python users, which is a substantial proportion of the people who code today, by the way. And also, on a more fundamental level, I kind of really enjoy learning about math concepts. Like, how good I am at math is a different story altogether. But whenever I learn a new math concept, what I would find is that, I would get something, I would be struggling with it, and something would click in my head, and then I would kind of get this like ephemeral understanding of it, and it would always be in the form of some visualization, some image that I would see in my mind, and then I would feel that, yes, I got this, and then I would go do other stuff, and then come back to it in, let's say, 2-3 years, and then I would realize that ephemeral image that I had in my mind is now gone, and then I would have to start building it up again. So this at some point I felt like, if I spend a little more effort each time, and make it like kind of crystallize that image, it's going to help me the next time I want to revisit that concept at the very minimum. And it might even help other people, because if it's something that helped me understand this concept so well, then maybe it can do the same to someone else's. It can have the same effect on someone else's mind who's struggling with the same kind of problem. And why Python? Well, that's, I guess, the easiest of those the three parts. um, it's just, first of all, it's obviously an awesome language, very very you can start developing with it very fast. It's designed to be as similar to pseudocode as possible. um, you like the user community of Python is awesome. So right now, like, if you just go to Reddit and look at the Python group subreddit versus looking at the subreddits for any other language, there's far and away more people on the Python subreddit. And not only is it big now, but I can kind of feel that it's growing at a very fast pace. Like today, when I interview people who are fresh out of college, no matter what they studied, computer science or applied math or statistics, whenever you ask them a coding question, they invariably start writing the code in Python. And the reason for that is that it's so much like pseudocode, and it's like really reduces the barrier to entry. So it's more and more becoming the first language people use, and then they kind of, even if they learn more languages, it's kind of something they default to. So if you want to gain some traction, Python really helps you with that. Saying that this is a tool in Python really helps you with that, and you have a high chance that other people are going to pick your tool up, maybe contribute to it. In terms of some of the other options for doing this kind of stuff, like rendering 3D objects, creating visualizations, etc. I haven't looked too much into alternatives in other languages. Obviously, there's the well-known ones like Maya, etc. In Python, there are a few options. Blender is one that has Python APIs. It's a software for rendering 3D objects, and Panda 3D is another. First one, which is Blender, is it's not like fundamentally a Python tool. It's a 3D rendering software that happens to have some Python APIs, and so you have to be intricately familiar with the actual software first. And Panda 3D is more towards developing games. So that's the reason I felt that the thing I wanted to do was not addressed by any of these existing tools. And I kind of felt there was a need for a new tool.
And I'm wondering if you can talk a bit about how PyRay functions and some of the libraries in the Python ecosystem that you leaned on to simplify some of the development. And I'm particularly interested in what you're using for actually displaying the images that are generated from PyRay.
Yeah, great question. So first of all, I try to keep the dependencies on external libraries to a very minimum. Most of what PyRay does, and I should have actually mentioned this in the in my previous answer about the alternatives, is more or less covered in a program called POV-Ray, and that's kind of it is kind of its own programming language. So in terms of like what I'm using to do these things in Python, there's a library called the Python imaging library, and it basically gives you these very primitive functions, which is, it lets you draw a line, it lets you draw an ellipse, lets you draw a plane with if you want to add transparency to the plane, it lets you do that. It lets you do image manipulation, like change the bytes of an image and stuff like that. So all like really basic image manipulation stuff. So I've been relying like mostly on that one library for the most part in terms of actually rendering the image. And I mean, yeah, I feel that I kind of I really feel that that's pretty much covers most of what I need to do. I don't feel a need to take dependencies on other libraries for most of my use cases. And then of course, like for the more mathematical aspects of Python, obviously, as we all know, has a very rich suite of libraries in NumPy and SciPy, where you can do all kinds of mathematical functions, machine learning if you want to, optimization, etc. So yeah, those I would say the three core libraries that I'm depending on right now are NumPy, SciPy, and Python imaging library.
And given the mathematical orientation of PyRay and your work as a data scientist, I'm wondering if you have found any use within your day job of the work that you've been doing with PyRay.
Yeah, for sure. So many times we have discussions within our group of we are tackling this, let's say, classification problem. So I wonder what technique we should use. Should we use support vector machines or logistic regression? Why should we use something complicated like support vector machines? So then, because PyRay has these, with PyRay, I've been developing these methods to kind of handle images. One example is that I can quickly pull up a quick demo where I let people draw like two categories, and then I can run the Python version of whatever the classification techniques are that we are debating, and then we can just visualize how they are behaving. So we are no longer playing this guessing game of, oh, what would happen if you gave SVM this kind of data, and what would happen if you gave logistic regression that kind of data. You can just draw it on an image, and then because I've been working on PyRay, I have the ability to, not just the ability, but I can very quickly interpret that image and visualize the results very effectively. Yeah, that's definitely, and there are many like this classification example is just one instance. There are a bunch of other examples where we are looking at survival distributions for machines in Azure, and we are like, okay, if the profile of the survival distribution looks like this, what will happen? So then I can quickly develop an application that will allow people to just draw it out and then show you the results in real time.
Are there any particular capabilities or use cases that are unlocked or enabled by the fact that PyRay is implemented in pure Python that would otherwise be either impossible or impractical to do as a Python developer with some of the existing options that you mentioned, such as Blender or Maya or something like that?
Sure. So PyRay is, like I said, fundamentally a library for creating these mathematical visualizations. So, for example, if you go to Google and type geometric GIFs, right? Or you can even go to the PyRay GitHub link, and you'll see some cool GIFs there as well. You'll see these really nice, cool GIF files that you wonder what they are. You're almost drawn into them. People have made some really beautiful mathematical artwork, but invariably when you start to dig into, oh, how did this person make this amazing piece of art, it's always in some obscure language with I've heard of people using something that's used for web development to create those images, etc. And they admit that it's just something that works for me. So that's something that I hope to change with PyRay, where here's a cool kind of visualization, and then right here is the Python code that you can, if you're a Python user, you don't have to, you probably already have everything that I'm depending on, and you can just paste this one line of code into your two lines of code into your console, one for importing and one for actually running the method, and get the same result that I got, that you see on your screen, right? That's definitely something that is, I would say, the initial use case of PyRay. I don't intend for PyRay to always be just a library for creating mathematical art. And there really is no, I couldn't find any Python library that's just for mathematical art. You can find mathematical libraries people have put together for creating mathematical art that are not in Python, and then you can find other libraries in Python that are geared towards visualization, but for different use cases. So like I said, Pandas 3D is more for developing games, so it's more of, oh, let me put a panda here and let me make it walk and let me rotate my camera in this way. So a lot of the nitty-gritty stuff is abstracted away, and so and that obviously limits the number of things you can actually do with it. I think the closest thing that comes to PyRay in that regard are Manim, which was the library that inspired me, and that's the library that the channel 3Blue1Brown uses. But I feel that I personally had a very hard time getting it set up. And then the other non-Python library is POV-Ray, which is this really old program and programming language that people have been using for a very long time, but then it's not Python. You have to learn it from scratch if you want some nice mathematical functions, you either have to code them from scratch or somehow learn to interface POV-Ray with those languages. And on that topic, there are also some libraries where you can actually try to interface POV-Ray directly with Python. And one such library is called Vapory, Vapory. But again, I tried that one out too, and again the limitations there are that first you have to learn this POV-Ray, which is like a whole different language. And second, it's again a pain to kind of interface it with Python. First, you have to get it installed, you have to have the right version installed, then you have to make your Python installation aware of the POV-Ray installation. That kind of, it's not trivial. Yeah, those are some of the alternatives and the use cases that that Ray is geared towards.
And are there any aspects of the work that you've done on POV-Ray in terms of building it initially or maintaining or evolving it that have proven to be particularly challenging?
So there have definitely been challenges in terms of building and maintaining a library like this. First of all, I have kind of no background in graphics whatsoever. So things like learning to shade objects in different ways as the lighting depends on depending on how they're interacting with the ambient lighting. How you change the RGB values. So for example, until like a few weeks ago, I didn't know that there was a HSL scale that's kind of exactly geared towards this use case where the L stands for luminosity. So you can just hold the H and S values fixed and just change the luminosity depending on how exposed to light your object is. So I kind of have to learn these things from scratch, which is always challenging. Then, like, if I want some kind of complex objects, right? Like if I want simple objects like cubes or platonic solids, like an octahedron or a dodecahedron, it's a kind of not that hard at all to just code it up. But if I want a more complex 3D object, like let's say a face or a pot or something like that, I have to somehow get this data for like a mesh plot of the object, which I am imagining as just a collection of planes that I can just draw, and then with the rotation capabilities of POV-Ray, just rotate it around, etc., and do what I want with it. So that's like getting that data for these different kinds of objects has been a challenge so far. Maybe I'm naive and there's just a very easy solution to it, but I haven't found a good one so far. Then, like, if you want to draw some characters, at one point I wanted to draw like a samurai, and then you wanted to move, you want to animate it. That's something that's very difficult to do from first principles, just animating these kind of characters in a very natural way. And I hope to get, and this is where I might need to interface with some good external libraries, because these kind of things are very hard to code from scratch. So yeah, these are basically the challenges I'm facing and hoping to overcome.
And when you're building a model or an image in PyRay, is it sort of a live coding interface where you can write the initial line of code to put up the first image, and then you can add additional code to manipulate it in real time as you're typing the code and manipulating the object? Or is it more of a sort of read, eval, print cycle where you write the code, see what it looks like, and then make another change and then re-render it and see what it looks like?
Yeah, currently it's not so much a real time phenomena. Although I imagine adding a functionality like that won't be too hard. But right now, just to keep things simple, it's just an interface where you have to write your images out. Right now, all it does is write images, and there are functions to write a series of images which change according to the motion you want to see. And then you have to actually use an external library called FFmpeg, or whatever you're comfortable with, to actually convert that series of images into a video or a GIF file, or something like that. So Currently, I mean, for most of my use cases, I feel that it's good enough, and it also keeps the library light, free of external dependencies. But it's definitely something I'll consider, some functionality I'll consider adding in the future.
And are there any projects or experiments using PyRay that you're aware of that are particularly interesting or unexpected?
Sure. So first of all, like I mentioned, I used it at Microsoft to create these interactive demos where you can test out, you can get user input in the form of a drawing they make on an image, right? So some kind of profile, or some kind of data they make on an image. And this could be easily generalized where you have this, like I can imagine having this website with all these demos. Things like that already exist, but I think that like a lot of different cool demos can be made that are not necessarily available now, especially with regard to probability. So that's the first one. And then another interesting one is physical simulations. So with PyRay, I've been developing these different kinds of objects. And for example, let's say you want to get you have a tetrahedron and you want to get the bin packing density of a tetrahedron. By that I mean, like, with tetrahedrons, can you fill up 3D space? And the answer to that is no. Like, there'll always be some gaps if you just put tetrahedrons, which are these four faced solids which have triangles for each face. So the question is, what is the maximum percentage of space you can fill with a tetrahedron? And That's something that, since I have all these 3D objects developed in PyRay, you can do this simulation, and people have actually done simulations in the past to break previously highest known bounds, right? They're like, okay, the current bound is like 70%, but hey, look, I did this simulation where I managed to pack 80% of the free space with tetrahedrons. So doing those kind of physical simulations. Another example along those lines is I was making a YouTube video about fair dice, fair dice, right? And that's one of the main use cases that I have for PyRay right now, is to create these mathematical YouTube videos. So now you have these kind of different solids, right? Like, you come up with this kind of new solid which you're not sure, is it a fair dice or not? And it's very hard to tell. So then, like, it's very hard to derive that mathematically. So again, you can do like a mathematical simulation where you can just simulate an environment where this object is falling on the ground and bouncing around, and that way you can get the probabilities of all its faces kind of touching the ground, and that will tell you whether it's fair or not. So those are some kind of unexpected use cases that you can use this tool for.
And do you have any particular features or improvements that you have planned for future releases of PyRay? And are there any particular skill sets or areas of help that you're looking for from people who would like to contribute to the project?
So in terms of future improvements, I think it's mostly stuff I talked about earlier in the podcast. So animated characters, I'd love to have that functionality. I'd love to have a bunch of 3D models of different kinds of cartoon characters, and also have the ability to make them walk around and do stuff. And along those lines, also like more complex objects like globes, so that you can maybe animate things like eclipses and flight paths, and stuff like that. Right now, as I said, the core piece of PyRay is rotations, right? So it's how to rotate these 3D objects. So and that doesn't have to be restricted to just three-dimensional objects. You can also do that with four and higher dimensional objects, and get a feel for the different properties of a four-dimensional cube or a tesseract, for example. And I actually have a video of that on my channel. Right now, the way I rotate these, I have a very rich suite of libraries of methods for rotating these three-dimensional objects, but I just have this one method for rotating higher like four and higher dimensions. So I plan to look into more interesting ways to rotate higher dimensional objects as well. Yeah, those are some of the things I'm looking to improve in future versions. And then the next part was what skills would someone need to contribute to PyRay? I don't imagine that there's a very high bar, frankly, as long as people have a basic familiarity with Python and know basic linear algebra. So as I said, PyRay is all about rotations, and the way I handle rotations is through rotation matrices. Now, if you in the industry, the more common way to go about handling rotations is through a concept called quaternions, which is this kind of analog of complex numbers. And just using rotation matrices is a much simpler approach, and you can actually extend it to higher dimensions, which is not so trivial with something like quaternions. Of course, there are disadvantages to rotation matrices as well, but you can imagine that that's like a core part of PyRay, understanding these rotation matrices. So like I think if someone has like some surface familiarity with linear algebra, and they just read the file where I have the code that does these rotations, it happens to be called rotation.py. I think they'll be able to grasp pretty quickly what's going on. Even if they don't at first understand how exactly it's working, they'll at least know how to use those functions as black boxes, since I feel like I've documented them well enough. Yeah, basic linear algebra and very basic Python, nothing fancy, is more than enough.
And are there any other topics that you think we should cover before we start to close out the show?
Well, yeah, I was having this interesting conversation with my colleagues here about Python versus some of the other languages, and kind of what's the quote unquote best language. So I just want to share some of the insights from that discussion. So I am kind of the odd one out in my team in terms of Python being my favorite language. Some of my other teammates are from a more traditional engineering background, and they are used to compiled languages like Java and C Sharp. In Microsoft, we mostly use C Sharp, of course. So, and they kind of surprisingly were not on the same page in terms of, Python being more awesome than those other languages. And the reason for them, the fundamental difference is that, Python is not strongly typed, whereas these other compiled languages like C Sharp and Java are. And that obviously gives you some strengths and weaknesses, right? There's some pros and cons. For example, like a pro of not being strongly typed, and by that I mean you don't have to explicitly specify the types of your variables. You could just say a equal to 5, whereas in C Sharp, for example, you'd have to say int a equal to 5. So you'd have to specify that it's an integer. So this makes kind of the barrier to entry for Python a lot lower. It makes it very close to pseudocode. And before Microsoft, I was a data scientist at LinkedIn. One thing, and I was in the growth team for their mobile app. And one thing I realized was that these barriers to entry really matter, right? You could have a form that users need to fill before they sign up for your website. If you put like a really trivial step in there, that's you feel that anyone who's come this far should have no issue at all doing this one more thing, maybe just taking a checkbox or something. They're they're definitely not going to kind of give up just for that little extra bit. But in practice, the fact is that when you're dealing with data for millions of people, every small step, no matter how small it seems, causes some drop off, right? And I like to apply that concept to programming languages as well. And I think this is the reason that more and more people are not only using Python but are getting into coding as well, because Python removes some of these barriers that by not being strongly typed and by being so close to pseudocode. So you have less and less drop off, less and less people give up on programming in general. And it's very easy to start projects, right? It's very easy to kind of, as I said, you'll find good communities, you can get people on board a lot faster. On the flip side, once a project becomes very large, then some of the advantages of these more strongly typed languages come to the fore. So because C Sharp is strongly typed, you can have like this really good development experience where you can just change like the name of a variable or a class in one place, and it's just going to, in the editor itself, Visual Studio, it'll change it everywhere, right? And those kinds of things are much easier those kinds of features are much easier to have in strongly typed languages. And where you have like a large team of 20 people or more working on a single code base, you have to design all kinds of unit tests, right? It just becomes so much easier when the language is strongly typed. When your language is not strongly typed, like Python, you have to account for all these. In your unit test, you have to account for all these other use cases where data that you're not even expecting comes up, is fed into your method, which you wouldn't even have to think about, because the compiler would take care of that for you in a strongly typed language. So just I feel that just feel that was a very interesting conversation we had. The takeaway from that was that for really large projects, like as projects become larger and larger, they just become easier to manage in these traditional strongly typed languages. But I feel that that's a good trade-off, because it's harder to even get to that mass where that critical mass where the advantages of a strongly typed language will even start to shine. And that's something that Python shines at, and in general scripting languages that are not strongly typed shine at. So it's kind of a paradox if you think about it, right? Because these kind of scripting languages are good if you want to get to a critical mass, but once you get to the critical mass, then these strongly typed languages become better. So yeah, that was kind of an insight I wanted to share.
Yeah, and that's one of the areas where the recent additions of the typing module and the type annotations for being able to actually enforce them, in a static analysis phase, allows some of these projects to continue to be viable as you do get to these larger code bases, because you can maintain that type information throughout the code base without it being as cumbersome as it can be in more statically typed languages such as C# or C++ and Java.
Yeah, and that's something that you feel will get better and better in a language like Python with time. But again, like my teammates were of the opinion that yes, it is going to become better and better, but it's never going to be at the same level as these strongly typed languages, because some of these features are just so much easier, and some of them might even be rendered impossible by the fact that Python is not strongly typed. But yeah, you can kind of rely on good doc strings and get better and better libraries. And actually, along that vein, another interesting aspect is that people don't like about Python is speed. You can get a really good speed in compiled languages, but since Python is a scripting language, that's a bit of a trade-off. And when I kind of posted about PyRay on Reddit, then that was something that I got a lot of comments on. People were saying that it's never going to be something that you can render in real time for something like video games or visual effects, and those kinds of use cases. And you have to have like bare metal, like C code to do stuff like that. And I agree that that's kind of the state of things now. But you can imagine that that's something that's going to definitely get better and better with time. If you compare the speeds of Python 3 with Python 2, you already see a big improvement. So hopefully that gap is going to close further and further. And as we know that the Python community is really large, and the growth is really accelerating. So that's going to push some of these improvements even, they're going to hopefully get us these improvements even faster. Yeah, that's kind of interesting to think about some of these like trade-offs.
Yeah, definitely. All right. Well, for anybody who wants to follow the work that you're up to or get in touch, I'll have you add your preferred contact information to the show notes. And so with that, I'll move us into the picks. And this week, I'm going to choose a series of books that I started recently by Fred Saberhagen, who I've mentioned in previous picks for one of his other series. In this one, it's a sci-fi series called the Berserker series, which is set in the sort of distant future where mankind is starting its expansion throughout the galaxy, and they've come up against these fleets of machines that were crafted, in the distant past by this other unknown race that were set with the task of exterminating all life in the galaxy. And so it's this series of books about the war between mankind and these emotionless machines that are just going about their task with mechanical efficiency. So it's an interesting set of books so far. With and Fred Saberhagen is a great author who I've enjoyed in the past. So if sci-fi is something that you're interested in, it's definitely a series worth checking out. And so with that, I'll pass it to you, Rohit. Do you have any picks for us this week?
Sure. So I'll start with something more related to PyRay, and then I'll transition towards something closer to what you said. So for my picks, I use PyRay right now for primarily for creating videos and blogs. Putting GIF files into blogs, like I mentioned. For the videos I create are on my YouTube channel. It's called Samurai Math. Some of them, because I was just starting out, don't have really good sound quality. But I think the visualizations on some of them, especially the ones with a higher number of views, are. And then the channel that kind of inspired me to start making my videos and creating PyRay was, as I mentioned, 3 Blue 1 Brown, and that's definitely like an awesome channel if you want to learn about maths and if you want to be good at maths. That guy is really good at creating these really rich mathematical animations and getting to the crux of like a mathematical topic that you just wouldn't have otherwise realized, even if you use it day in and day out. And then transitioning to the topic that your sci-fi book was about, Tobias. There's a very awesome channel it's the channel has the creator's name on it, which is Isaac Arthur. So just look him up on YouTube. He talks a lot about how humanity is going to survive in the long term, what strategies we are going to use, how we are going to survive, the sun expanding and engulfing the earth, and all the stars in the universe slowly fading away. And one kind of interesting tidbit is that when we'll have this state in the universe where there'll be just black holes left, we'll actually be able to prolong our life, if we play our cards right, to a much longer time span than the total lifespan of the universe with stars in it. So the time of the stars will just be kind of an interesting backwater, and the true extent of civilization will be realized in this era, in this post-star era. Definitely something along the vein of sci-fi, and definitely very thought-provoking. Those would be my picks.
All right. Well, I appreciate you taking the time out of your day to join me and talk about the work you're doing with PyRay. It's definitely an interesting project and one that I can tell you've put a lot of effort into, and I'm sure a lot of people are going to be able to get some benefit out of that. So thank you for your time and the work that you've been doing, and I hope you enjoy the rest of your evening.
Thanks for having me, Tobias. It was a pleasure.